Here's a catalyst called platinum. It has a pear shape to it. You could search an internet for images of a pear-shaped nucleus, like barium. This is platinum here, but you could look for barium, radon, and radium. They've experimentally shown that nuclei have a pear shape for those. So their magnification of their equipment is about 0.5 trillion x. This is about 100 times that resolution. 50 trillion x magnification here of platinum. The brown protons and white neutrons are also going to be shown for vanadium, another catalyst. Of course, platinum is the ultimate catalyst, and it has a certain shape. It has a ring. You can see it here. I'll point it out to you. Yeah, this is the back side. There's a ring you can see there down, not on the top, but the next tier down is the big ring of 25 protons in a big ring. And the other side is the hook. You see the top of the hook there, and the center of the hook is the axis. Okay, there's the hook. Now, when we go to vanadium, you'll see that I'm trying to show that it also has a hook, a ring, and an axis. So let me back off a little bit away here from platinum, and I'm going to show you some of the larger models of argon, and we're going to build up to vanadium, which adds 5 protons on top of the argon foundation. All right, so today's lecture is on the vanadium catalyst, the hook in a ring, like platinum. There's a hook inside of a ring. And it's based on argon. Now, vanadium is element 23, and argon is number 18. So argon has an isotope number 40, and also if you add another proton to it, you'll get the potassium 40 is available, and if you add one more to that, you can also have an isotope 40. So I'm going to take a look at the periodic table here as I switch the camera over. Okay, there's argon on the right there. This is a silhouette of argon. It has the cube in the middle, and then it has pyramids on the top and bottom with 3 layers. And then, like carbon, it has a single proton on the left, right, front, and back there. And so then if you add some more, you'll get to different sections of the periodic table. I'll show you now. Yeah, we could go to the left over here more. And then we see the series that comes from potassium is built on top of argon. You see there's 1 blue proton added on top there. And then calcium, there's 2 more, scandium, titanium, and finally vanadium is our goal here. See there's 5 blue dots there, where that means there's 5 protons added on top of argon. So I'm going to be using small styrofoam models for you here, and I'm going to show you what that looks like here too. So like I was saying, argon is a foundation element, and vanadium is an incremental element. I'm going to go to the next slide now. The projectionist was a little slow there. So the rules for charge distribution are going to be used. Not only am I building up these pyramids, like in that silhouettes there from the periodic table, but also the charge distribution of where the proton goes. And the rules are basically that protons form lines of protons outside of the cube. Inside the cube, protons repel protons as if they have some kind of electrostatic repulsion. And then placing the neutrons onto the nucleus, you'll see in a couple minutes, the neutrons fuse down into the lowest pits of argon. And it's quite a porous type of element. Now I'm going to be switching over to the styrofoam spheres. So I could have used hexagonal close pack for these nuclei at the center, but I decided to use a cube. So I discovered on May 25th, 2017, that iron has a cube with 3 layers in the center. And the white protons on a 3-layer cube go as far away as they can. So now here's the 2-layer cube, and you can see that for argon and carbon, that the protons are as far away from each other as they can get. And this is a survivor. So that's why the cube is so good at the center, because then it's covered with hexagonal close pack. Whereas if you had made nuclei candidates in a star that had the hexagonal close pack in the center, then the exterior would not be armored. It would be more of a cubic place with large gaps. So you can see the gap here, which is important for the physics, that the large gap in the cube is about 4 times as big as the gap in the hexagonal close pack. All right, now on top of the cube, we get carbon. So now this is just the cube with 4 more protons put on top of it there. There's the carbon. And that's in the center of argon. And let's see, here's nitrogen, for example. We're going to skip over that. We're also not going to be looking at hydrogen, and we'll not discuss boron at all. Now, on top of carbon, then, I'm saying that we're going to make argon. And like the periodic table showed you there, we need 2 large pyramids, and then that's it. All right, there's the 2 3-layer pyramids, and each one has say it's like a lithium 5 on top of another square, and each one fits together. They nestle together like stacking up cannonballs in a square pyramid. That goes on top of the cube. And that nestles onto the cube securely, and that's a good survival type of shape there. And now, you can look at the recipe for doing this on the internet. I have this website that I'm going to show you now. And I'll move the camera over to that. Oh, there you can see the pieces of argon. There's the cube, 2 squares, and then the 3-layer pyramids of protons in green. And that all gets put together to make the final nucleus. So this is argon 40, and we're going to be making potassium 40, and potassium, calcium, all have an isotope 40. So we're going to take advantage of that right now. Great, so here's the argon we're putting together. There's carbon with a pyramid under it, and here's the final pyramid going on top of the carbon. And that's argon. And it all holds together like stacking a well-fitting machine. And it's longer than it is wide, and it has 40 little spheres in it, and we have to, now to go to potassium, I'm going to change one of these over to, from a neutron into a proton. So I'll just pick one here, like where my thumb is, and I'm going to change that into a proton to get calcium, and to get potassium, I mean. And then the other one I'm going to change over here, on that side, to get the calcium 40. So we're not adding any, we're just replacing. Take this neutron off of the argon. And change it into a proton for potassium. And then that goes back on to carbon. Of course, it all works together. But now we're going to work our way up towards calcium now from this. So that means the other pyramid we're also going to add, we're going to change this neutron into a proton to get calcium 40. There, we changed that one over. So I'm going to take a second and put them together with little toothpicks on this live streaming free video on YouTube. Thank you for the live streaming service there, YouTube, because I'm going to just put this together right in front of the camera. a three-layer pyramid with the correct number of protons and neutrons. All right, you can hear the styrofoam. All right, so then once we have that put together, I'm going to go on from calcium into scandium. And I have to have the correct number of neutrons added on top of calcium-40. So for that, I'm going to have to look up some numbers here, the isotope. So I'll show you how that goes. Okay, I got my notebook here. Here, you can actually look at it and make a photograph of the recipe for making vanadium 51. All right, you can see we got the carbon 12, argon 40, calcium 40, potassium 40. Now, to go to scandium, I have to add 4 neutrons and 1 proton. And then when we get done, it'll look similar to manganese, so I'll show you right now. So here's the manganese 55. It's element 25. It's 1 less than iron. And you can see the argon pyramid up here on the top, these 3-layer pyramid from argon. And it just has added protons and neutrons, and it creates some rings, 10 protons in each ring. And then when we get to vanadium, you'll see that one ring is not complete and it's a hook. So now I have to now point the camera at the thing I'm talking about. And here's the manganese 55 that I was just discussing for you. And there's a ring there of 10 protons in white. And the brown neutrons. And then on the other side, but they're not coaxial, another ring that's been ruined by proton number 25 there. So that, like copper, it's non-ferrous. One ring has been ruined. And it's not coaxial, so it is just not ferromagnetic as a element. But in a compound, manganese can create ferromagnetic compounds, which I've never seen in person. I guess they're thin films. So getting back to the thumbtacks, I'm just going to do a little work here for you. Okay, that kind of fell apart there, so I'm going to just move over to this picture here. And what I'm going to be doing during the remaining 10 minutes of today's live model making, you're going to see that one ring of protons forms on the vanadium surface, and the second ring is uncompleted, so therefore it is hook-shaped. It's lacking one proton, so it will have a possibility of the itinerant proton current can depart the nucleus here, go to a faraway atom or molecule, and be a catalyst there, and then the proton current would come back into this hook at the other end. So that's the basic concept I'm working on here. And so there's a lone proton called the axis, and let me just show you where that is here on this older model here. Yeah, there's one in the middle, marked number 19. So it's in the middle of the ring. That is not on the cube, actually. And it's called the axis. And if you took away, for example, this proton here, it would make a hook shape. And so that vanadium, in other words, will look like this. If I had put together that other model, it would have shown that this ring didn't get completed. There's not enough proton white balls here to complete this ring. It's a hook. So just like platinum, which I was showing you, there's a axis inside the hook and then another ring on the other side. So let me show you that one more time there in a sketch. So, for example, if I would pick up the platinum model and make a sketch of it, here's what that sketching live video would have looked like. All right, so there's the sketch of platinum, which shows the hook in this middle, an axis in the middle of the hook, and a big ring of 25 protons around the outside. And it's kind of a pear-shaped nucleus, as you see, bigger at the bottom. And the exterior is all hexagonal close pack. It's a real survivor. It's a fossil from eternity. Let me turn the point of it straight at the camera so you can see how well armored it is for any incoming. It's teardrop shaped, raindrop shaped. All hexagonal close packed, armored for a surviving nucleus. And then the hook is shown on this side here for platinum. All right, so that's the theory here. You see the in the background the pear-shaped nucleus of platinum. Now, vanadium then has been shown to have this hook shape available on it, and the ring and the axis. So I'm hoping to make some kind of invention from that in the future. And let me just say, what would that be? I could use platinum, which is like $30,000 a kilogram, or I could use vanadium, which is very inexpensive, say $10 a kilogram. And so solar cells using magnets and water electrolysis, nanotechnology magnets using, say, anti-ferromagnetism, and of course the goal is to produce electrons popping out one end of the battery, the fuel cell or something, and hydrogen coming out the other end, so that the vanadium would crack that open there. Now, you can go to the ARGON website I showed you there, and that was at the pyramidalcube.blogspot.com. And thank you very much for joining in today, and I'll be back again on Monday, 10 a.m. I'm going to look at the messages. Let's see if anybody talked to me on this message board. No, I don't see anything. So I'm going to end the stream now. Thanks a lot. Bye.